The concentration of distribution of statistic T of x around its true value f of theta is high when mean square error is low, but the converse is not true. So the first statement is true because if we consider the Chebyshev's inequality, so first we have MSE of theta. So MSE of this theta is nothing but expectation of t minus this f of theta whole square. And by Chebyshev's inequality, probability of mod t minus f of theta greater than or equal to epsilon is less than or equal to MSE of t divided by epsilon square. So for a small MSE, it forces a smaller tail probability for every epsilon greater than 0. So that means low MSE implies that the distribution is concentrated around this f of theta. So the converse need not hold because we can have very high concentration but a very less probability of huge outliers. So that means for example, if I take t as some f of theta with probability 1 minus epsilon, and let's say f of theta plus 1 by square root of epsilon with probability epsilon. So if I find probability of mod t minus f greater than delta, so this is less than or equal to epsilon, so this can be made very small, so that means highly concentrated, while the MSE would be sigma into 1 by square root of sigma whole square, so which is nothing but 1. So that is not small, so therefore statement 1 is true because converse is not always true. Now if we consider the second statement, there exists no estimator for which the mean square error is least for all epsilon belongs to theta. So this is also true in general because there is no estimator that has smallest MSE simultaneously for all theta. So a simple example can be, for example, if we are having x follows normal mu1. So if we compare two estimators, let's say x1 is t1 is x bar and the second estimator is 0. So if we consider the MSE of this t1, so that's nothing but variance plus bias square. So bias is 0 but variance is 1 by n. And if we consider the MSE of t2, so bias is mu square but variance is 0, so this is mu square. Now for mu small, so if mu is small, this t2 can have smaller MSE, or if mu is large, t1 is better. Hence there is no single estimator uniformly minimizes MSE for all theta. So therefore second statement is also true. So both statements are true.